In this video, we'll start with our third chapter on vehicle handling performance. The term handling or handling performance refers to the lateral dynamics or cornering behavior of a vehicle. The precise performance objectives are not very specific. They can be roughly summarized as follows. First, the responsiveness of the vehicle to driver inputs, which in the case of lateral dynamics corresponds to the steering input. Second, ease of control by the driver, especially in case of external disturbances to the vehicle. Third, there should be an intuitive recognition of the handling limits of the vehicle by the driver, and these limits should be recognizable early enough. And fourth, the impact of changes in certain vehicle parameters, such as passenger loads or loads in the trunk, different tires, or changes in the road surface on the vehicle dynamics should be kept as small as possible. In general, vehicle handling measures the performance of the vehicle-driver combination, which is also called the closed-loop performance. As you can imagine, however, this is very difficult to examine in practice. That's because drivers are human beings, and as such they are, first of all, very difficult to model, and second of all, every human is a very different driver. And hence, usually only the dynamics of the vehicle itself are considered, which is referred to as the open loop performance of the vehicle. The block diagram shown here illustrates once more what is meant by closed loop control. In fact, it resembles closely to the classical control loop where the vehicle represents the plant and the driver represents the controller. The reference input to the system is given by a reference path. So for instance, this could be the lane center line that the driver would like to track. And the output of the system is the actual vehicle position. The control error is then given by the tracking error of the vehicle with respect to the reference path, and it corresponds to the coordinate E in the path frame. The driver, as the controller, will first of all recognize the tracking error and then react to the tracking error by adjusting the steering angle delta. So for example, if the tracking error is such that the vehicle is to the left of the desired path, then the driver will steer more to the right. And if the vehicle is to the right of the path, then the driver will steer more to the left. As always in controls, there are disturbances acting on the plant, in this case the vehicle, which prevent the vehicle from following the reference path perfectly. And that's besides any deficiencies that the driver may have as a controller, in the sense that the driver himself will not be able to track the reference path perfectly. Now, as we have been saying, it is indeed desirable to examine this closed loop system, including the driver and the vehicle. However, our model of the driver is generally poor, and that's why it makes little to no sense in practice to study this closed loop system, especially in normal driving situations. When looking at critical driving situations instead of normal driving situations, the case is a little different. Here, driver models do make sense to some extent. For example, you can model the reaction time of the driver as a time delay in your driver model. However, the whole field of driver modeling is very complex and requires a very special set of skills, and hence this whole field is not considered in the content of this course. So instead, in this chapter, we will go on to examine important dynamic properties of the open loop system, which is the part marked with the red line up here, and whose input is a fixed steering angle delta, and the output is the vehicle position. Naturally, this leads us to the important concepts of vehicle stability and understeering oversteering, which we will look at in the next videos.